And there it goes. Attempt 2. Torque. Oh, that's much better. They can see now what I'm doing. There's no way they could see anything on the other video. I actually posted the other one, but I'm not sure why. So this is a better version. Torque. Well, torque on a dipole, I guess. Torque on a dipole, electric dipole, is what we're going to look at. So, okay, so what we need is an electric field. It's interesting. I can like see myself now that it just takes up the whole screen over there while I teach. I can kind of teach myself that way too. It's weird. Electric field, so it points to the right. Well, it doesn't have to point to the right, but you need some electric field. What we're going to do is we're going to say that this electric field is constant, so it doesn't change. Its value remains the same. I'm going to put this here, constant. All right, so the electric field is constant and doesn't change. And then we're going to place some charges in it. In fact, what we will do is we're going to place the dipole in it. Dipole means that, an electric dipole means that you have an object and the object is positive on one side, negative on the other side. So I could make a dipole out of a paper. I could probably just use this because I think we're almost done with that. I'm going to place a positive side on one end. Here's a plus. I'm going to put minus on the other end. And there, this paper is now an electric dipole because there's minus on one side and plus on the other side. So anything that is somehow, anywhere that you have a separation of charges, you will end up with a dipole. Now, specifically, we want the two charges to be the same. And what I'm going to do is I'm going to place negative here. I'm going to put positive here. And let me just add to it. So make sure that that one is also in the electric field. We have these two charges. They're the same. So I have Q and I have Q, identical charges. And then what we want is we want these two charges to be connected. So maybe some kind of a rod that connects the two. Right? Typically, it would be a molecule where you have the whole molecule. One side of the molecule is negative, the other side of the molecule is positive, but the negative is the same magnitude as the positive. So typically molecules, some molecules will be dipoles like that. But anyways, negative charge, positive charge, some distance between the two. Trying to think if I should do it the same way I did it with the other class or just simplify this. But so there's a separation between the two charges, and that separation is D, right? Yeah, leave it. Right, if you have an electric field, and within this electric field, you place a charge. So here's the electric field, and you put a positive charge in it, Q. It will feel a force. Right? You take a mass, you put it in a gravitational field, it's going to feel a force, gravitational force. You take the charge, you put it in an electric field, it's going to feel an electric force. Now, in which direction will the force act? Charge in the field, the way I drew it here, in which direction will the force act? You kind of have a 50% chance you get it right. Ha! Wrong. Which means the other option was right, which is what you were pointing out the first time. So, so yes, it's going to point in this direction. The force will point in this direction. On the other hand, if I were to place a negative charge, the force would act on it in the opposite direction. So if there's a negative Q, then you would have force pointing in this direction. Now you can either memorize this, that the positive charge, force on the positive charge in the electric field always points in the same direction in which the electric field points, and vice versa for the negative. Or you could kind of deduce this way. If the electric field points in that direction, then perhaps there's some kind of a large positive charge here, because it's the positive charge that sets up electric field pointing here, right? Or maybe there's some kind of a large negative charge on this side, so that negative charge sets up the electric field pointing in this direction. But it doesn't really matter whether you have a plus here or you don't have a plus here, but you have negative here, or you don't have a negative here, but you have plus. Doesn't matter. In either case, it's easy to see that repulsive force, hence the force points in this direction, attractive force, hence the force points in this direction. So you could, if you don't know, if you forget in which direction the force points, when you place a charge in the field, just add some charge to it. So looking at this picture now, right, I have an electric field that points to the right. This is as if I had some kind of a big positive on this side. And from this, I can deduce the direction of the forces. I'm going to have a force produced by the electric field that points in this direction. Here's force, let's call it F1. And I'm going to have a force acting on this thing that points in this direction. Here's F2. I'm going to get rid of this charge on the left-hand side because I don't need it. I only used it to deduce the direction of the forces. So now I have F1, I have F2. And what I can do with this is I can determine two things, the net force and the net torque. It should be easy to see that this dipole is going to move in a very specific way. If the force points in this direction on that edge and the force points in this direction on this edge, what's going to happen to the whole dipole? It's going to spin, right? It's going to rotate, and the rotation is going to go like that. Now, if you have rotation, then that means you have a torque. So there's some sort of a torque. We have to calculate that. All right. So let's do the net force first. F net on the dipole. This may or may not be useful in some problems. I don't think it's going to be useful for the problems we're going to solve today, but it may be useful in some cases, some other problems. F net, by definition, on the whole dipole, F net is just the sum of all of the forces. Well, how many forces do I have acting on it? 2. F1 and F2. We're ignoring the gravity, right? There's no gravity in the picture. So I have F1 plus F2, and that's all I have. But what can you say about F1 and F2? They're equal but opposite, right? So they're exactly the same in magnitude, but they point in opposite directions. So I might as well write F1 minus F2, and that amounts to a big 0 because F1 is F2, in magnitude at least, right? So what's the net force on a whole dipole? 0. What that means is that the dipole will never accelerate. And in fact, if you just leave it here without pushing it at all, if you just leave it there, it's going to sit there. It's not going to travel to the right. It's not going to travel to the left. It's not going to travel up or down. It's not going to do any of that. It's just going to sit there, except for the rotational component. So anyways, net force 0. We can put it down here. F net is 0. So you will get no acceleration out of this dipole. But now let's look at the torque. We know we're going to get rotation here. Right, this thing is going to rotate like this. Since we get rotation, there's got to be some torque, so let's look at that. Now, in case you forgot, the equation for the torque is F times D times the sine of the angle theta. And to give you a picture that goes along with this, let me move the camera because you may not, usually in that corner of the board, you don't see too well what I'm doing. So equation for the torque is FD sine theta. Picture that goes along with this. If you have a board, you provide some kind of a pivot here, you apply force like that, you're going to get this thing to rotate. Now, what's D? D is the distance. D is the distance from the axis of rotation, or the pivot, but it's really the axis of rotation, to your force, whatever you apply the force. So this is D. And then the angle theta, that's the angle between F and D. In case you forgot, right? So now you have all of that. This is the torque. And so what I need before I can calculate anything here, before I can move forward, is if I'm going to write some expression for the torque, then I need my axis of rotation, because torque is always relative to some axis. And it's good if we can match the axis in our equations with a real physical axis of rotation. Where is the axis of rotation in this case?
In the middle between the two.
It's going to be right in the center, right? This stuff is going to spin like that. Axis of rotation is right at the center. So I'm going to put this point here. And this point is going to indicate the center. This is going to be my axis of rotation. Now, here's a force. That force relative to this point is distance d away. But I'm going to call this distance d over 2. And you'll see soon enough why. And then this force here is distance d away from the center, but again, I'm going to call this distance d over 2. Obviously, what I'm doing is I'm setting up the whole separation as d. Right, d over 2 plus d over 2 gives me d. So it will make sense to do that when we run the equations. The other thing is the angle. So if I extend this out, here's my angle theta between d and f, and if I extend this out, here's my angle theta between D and F. And what can you say about the two thetas? They're equal, right? The two thetas are the same. We will need one more angle later on. I'm going to put it on the board now, and I'm going to erase it. But this angle here is also theta. So that angle, and this angle, they're all the same. We will need this, but not now. So I'm going to erase it. Just keep in mind that that's, you know, that's there as well. All right, so let's calculate the net torque on this whole dipole. Let's figure out how this thing is rotating. So I'm after the torque now. Net torque, by definition, is the sum of all of the torques. And I have two torques because I have two forces spinning this thing. So I'm going to have the torque produced by F1 plus the torque produced by F2. Now, do both of these torques give me the same kind of rotation? Or do they oppose each other? The same kind of rotation, right? The torque produced by this force will cause clockwise rotation, and the torque produced by this force will also cause clockwise rotation. So I can just add them up. I don't have to subtract one from the other. So let's take the next step. Net torque then is F1 times d over 2 times the sine of the angle theta plus F2 times d over 2 times the sine of the angle theta. But F1 and F2 are the same. So I can just add. So there's really no reason for me to have F1 and F2. I'm just going to label this as F and F. And therefore, I will get the net torque is, well, I add this all up, I end up with Fd sine theta. Right, F1 and F2 are the same, and then I have d over 2, so I just end up with that. Okay, now the next thing I'm going to do is that there's an equation for F, and that F is Q times Z. You take Q, here's a Q, you place it in the electric field, there's a force in it. So I'm going to replace an expression for the force with charge and the electric field, and I think this is it. So Q E D sine theta. Here's your equation for the net torque. And what I'm going to do is I'm going to erase this picture. I'm going to put a different one on. It's going to be the same, but it will be a little simplified. Remember when I did this angle here, theta? All right, so that theta is the same as this and that, right? Okay, so let's redraw it now. So here we go again, electric field. We want this electric field to be constant. We have a negative charge. We have a positive charge. Here's D. We're going to label D as a vector, and D always points from minus to plus. We're going to say Q up here, Q down here, and then the angle theta is this. And now you have the equation that corresponds to the picture, and the picture is a little clearer to see. E is the electric field, Q is the charge, D is the distance between the two, and then the angle is the angle between D and E. Right? So I'm going to put here theta, angle between D and E. All right, let's give you a second to look at it. And if you are all set, then you can grab the books and we'll just go ahead and solve some of this stuff. On page 680, I think, I can't remember that. So page 680 in your books, 680. What I'm going to do is I'm going to transfer the equation here so that I have net torque is Q E D sine theta. Sometimes, actually very often, Q times D becomes its own variable called the dipole moment, but I just don't think we need it, so I'm not going to put it there. We certainly don't need it for anything we're doing here. And so page 680, I'm going to solve number 30 something with you, but I don't remember what it was. Let me see, 34. So I'm going to solve number 34 with you. We'll do this one together. And then after that, you will have 36, 35, and 34. Well, that doesn't make sense. 36, 35, oh, and 37. Okay, so 36, 35, and 37. These are yours, right? So these are yours. This is what we're going to do together, 34. So the good news is that the problems with torque are very straightforward. In fact, the book only lists 4 problems, and I think one of them is not even on torque, which is interesting. But anyways, 34. 2 small plastic spheres, charge 17 nanocoulombs, are connected by 25 millimeter long insulating rod. Suppose the dipole is placed in the electric field. What is the maximum possible torque? Let's draw it. Actually, I have already a picture here. I'm just going to use that. This is going to be my picture. But now what I have is electric field. The value of the electric field here is 7.4 times 10 to the 5th newtons per coulombs. I have Q, which is 17 nanocoulombs. So let's put that here. 17 nanocoulombs is given to me. And the distance D is 25 millimeters, right? So D is given to me. Let's put it here in a picture as well. I want to get rid of that. I'm just going to put it like this. D is 25 millimeters, so 0.025 of a meter. That's the separation between the 2 charges. Now, so this is the setup for problem 34. The question is, so the unknown is, I'm going to state the unknown here. The unknown is the maximum torque. Right, calculate the maximum torque. So you have to do a little more thinking here. It's not just plug in. It's almost plug in and get the answer, but not quite that. Equation for torque is Q E D sine theta, right? That's the equation for torque. So let's plug in whatever we have and then see what we have to figure out. Q, 17 nanocoulombs, so 17 times 10 to the minus 9th. E, 7.4 times 10 to the 5th. D, 0.025 times the sine of the angle theta. So I could calculate the torque if I could figure out the angle theta. I have to determine what the angle theta is. Now remember, what they want us to calculate is the maximum possible torque, right? The value of torque goes from 0 to some maximum. At which angle do you get 0 torque? 0, right? When this thing is horizontal, then you get no torque, because when this thing is horizontal, let me maybe draw it here. If your torque, if your dipole looks like this, within this electric field, then the 2 forces that you have are doing this. Here's one force, and then here's the other force. Well, these 2 forces won't rotate this thing, right? It's not gonna happen. So in this case, you would get 0 torque. At which angle are you going to get maximum torque? At 90. So if you have a plus here, this goes down, you have a minus here. Let me draw one more. 90 degrees. In that case, you're going to get maximum possible rotation, right? Because you're going to end up with just maximum possible rotation. In fact, if you look at the math here, sine of 90 is maximum, has a maximum value there. At 90, it's 1. Sine can never be bigger than 1. And it is 1 at 90, so 90 does the trick. So we're going to put here, we're going to turn this thing into a maximum torque by changing the angle theta to 90. That's just 1, so you only have to really multiply this out, and then sine of 90 is 1. And you get whatever you get. That's easy to do. Newtons, units are newtons times meters. That's kind of it. I mean, that's, yeah, that really is it. So once you're set with this, I'm gonna have you work on these problems here, 36, 35, 37. I don't think I'm gonna put you into breakout rooms. You can probably just work on this stuff without the breakout room and then ask each other to see if you're getting the right thing. We'll go over the answers too. For the 2 of them, 35 and 37, you have answers in the back of the book because these are at. For 36, you don't. Okay, I'm gonna stop the recording and then I can probably post this thing. Let me see.